Bueno, yo también sí lo hago en castellano, voy a torturar a la vez castellano las matemáticas, así que intentar no torturar a nadie, así que lo haré en inglés. Okay, so I'm going to talk about what I'm most excited about, which is unsurprisingly my most recent thing, which is an archive and which is called variational dual solutions. For incompressible fluids. So this is an archive, and this is joint work with AMAED and Bianca Stropoli. Okay. So Bianca is a mathematician, a calculus of variations and regularity person at the University of Naples, and AMAED is an engineer in the civil engineering department at Carnegie Mellon. But he is one of those more mathematically inclined persons, and we were overlapping at Household Institute, and he was telling me about a scheme he developed for calculating, they like to calculate things, right? The engineers for calculating solutions for a system of, for complicated system. They really have complicated system of linear plasticity, right? So you can define some sort of solution for those, but the trouble is with calculating them. And the main advantage of the scheme he developed is that it allowed to get a variational structure for virtually any type of system, even if it doesn't have a priori a variational structure, like the Euler or Navier-Stokes. They don't have a priori variational structure, and using this variational structure you can do calculations easier because you have these kind of gradient descent schemes, right? And the point where he caught me, because my interest is, he was saying, look, my scheme generalizes some work that Brenier did. So, okay, let's have a look. And it turns out that it's a very interesting scheme overall. We're still exploring it. What we can do is to construct these solutions for Euler Navier-Stokes, use them to show the implicit limit of Navier-Stokes to Euler, of course, on the torus, so that you don't worry about boundary conditions. Yeah. So this is these are the early days of this construction, but it's quite a rich scheme, and I'm gonna present you the basics of it. So I really took Rafa's invitation seriously in the sense of thinking of this as a course. And so this is a very gentle introduction to these ideas. So anyway, this is a strange, non-standard piece, so it's better to do it slowly rather than quickly. So yeah, I'll essentially present the basic ideas then tomorrow. Okay, so this being said, let's do this thing on, let's say, call this variational dual solutions in a simple setting. Okay, so it goes like this. Take A to be, some operator that's from Rn into R capital N, and you can have really any type of relationship, either greater than little n greater equal or less or equal than capital N, and you are interested in finding, say, zeros. Yeah. So of course the simplest case is when you have something like this, so the linear case, yeah. And then I'll use continuous without comment the Einstein summation convention, namely when you have repeated indices, you sum over them. So then I is an index that goes from 1 up to little n, and alpha is an index that goes from 1 up to capital N. And then when you have such a system, it can be underdetermined, overdetermined, so you can have no solutions, you can have many solutions, you can have one solution. Okay? So the goal is the following. To construct a string list, which I'm going to call dual function, whose critical points are zeros of A. Yeah. Okay, and why is better to have critical points? Well, actually, what is even better is to have extremizers or minimizers, right? Because there is more structure in those things. For one thing, you can have some sort of a priori estimates just because if it's a minimizing of an energy, then it's lower than any competitor for that energy. And then you have the second variation, which is positive definite. So there is definitely more information apart from the computational advantages, right, in using these gradient flows for computing things. And our hope in some sense is that we'll be able to use this machinery to provide an alternative perspective over these wild solutions for Euler, which are obtained for convex integration. But we're nowhere there. Yeah. Okay. So
how does that work? What's the idea?
I'm not sure.
Okay.
Okay, so you construct a dual functional, and how do you construct it? So define SH, and I'm going to put a hat here of the variables x and z, and I do it like this: z alpha a alpha x plus h of x. Okay, so summation of repeated indices alpha goes from 1 up to capital N. Okay, and requires that. Its derivative with respect to x dsh hat with respect to some xi. Yeah. So I'll just differentiate it here. Okay, and require that this derivative provides an x for any parameter z. Yeah. So this is like a function, these are like functions in x, and I have this parameter z. And what does this mean? It means that I want to have something like this, i.e., there exists x h of z such that I have the following z alpha d alpha dxi evaluated at xh of z plus dh dxi evaluated at xh of z is equal to 0. Right? So I want to have this thing. Okay? And there is freedom in choosing this h. I mean, this looks very general, but we'll settle on some very specific h in the case of Euler. Okay, so now if you have this, then what is this buying you? Let's see. Let me just erase this. Because if you have this, then define the dual function. Which is like this, sh of z, yeah, should be related to this, namely it will be sh hat of x of z, comma z. Okay? And now if I take the critical points of this, then I'll be in good shape. Namely, what happens? I take dsh z d z beta z. Yeah? Okay, so this is, okay, it comes something like this. D z alpha d z beta, which is delta alpha beta a alpha d alpha dxi. So this is really a beta x z, yeah, plus I have now this part here, and then what I'm going to do is to take dh. Let's see. Now I also have this part to differentiate. So I have d alpha dx. Here I times d x I d. Let me do it like this because it's easier when you see it. Now, and then there is also this z alpha here. Okay, so just change the rule. And the good thing is that this thing here is precisely this star from here, so this is equal to 0. So what I'm left with is just this a beta x. Yeah. So critical points of this thing are just providing me zeros of this function.
Oh, okay. So, okay.
Yeah?
That's how you cook up.
Yeah, that's how you create this dual function. Dual function, say, whose critical points are providing you zeros of the original thing. Okay? Think of, say, Lagrangian, and yeah, you want to have some bigger function which does a trick for you. Okay? Questions? I'm going to erase this, yeah? Okay, now, the the Euler part, yeah? Okay, so we call incompressible Euler. In dimension 2 or 3, or higher if you wish, which goes like this, and again I'm gonna write things in coordinates because I like that better. Is equal to 0, and this is, and I'm going to work on the torus, which I'm going to write it like this. So this is RD. Okay. So periodic boundary conditions. So R plus I'm gonna take the divergence precondition now and initial dot bi of x. This is equal to bi x. This is again. And I'm gonna construct the version first, the version of what was SH hat, yeah. And the way I'm gonna do it is to go through the weak formulation. So in particular, I'm gonna multiply this in here by some function lambda, which is really a vector. This decomponent. Yeah. Let's say it's C infinity. Okay. Yeah. And it's divergence free, and at some final time capital T is equal to 0. Yeah. And I'm going to use another test function here, which is gamma for this equation, which is, again, small. And now I'm going to define this S hat H of V lambda gamma, and I'm going to put another function, which I'm going to call V bar, you'll see in a moment. And it's going to be something like this. Yeah. So what am I doing? I'm multiplying this and I'm integrating by parts. Yeah. In time here, and then I have vi vj, and I should get this. Yeah, let me make it look more complicated. Yeah. So because these are dummy indices, I can switch I and j and I get the same thing. Okay, so this is dt dx plus. Okay, when I'm integrating in time, I'm going to get some boundary terms, and because of this condition, I'm just going to have the initial data now. I'm not going to have what happens at time t. So I'll have this vi x lambda I x 0 x. Okay, now what will be my h before, and this is going to be this thing here. So h in principle is a function of the unknown v, and also of this v bar. Yeah. dt dx. Okay. And in practice, we'll just focus on the following. h v bar is just 1/2 of a v. This is a number, v minus v bar squared. If v bigger than 0, and v bar is something which is just in L2 in time and space. Yeah. And I'm going to call this a base state. So, why a base state? The intuition for this, based on the numerics that were done by Amit and his group, is that whenever you have more solutions, you have non-uniqueness. So like for burgers, because that's easier to simulate. This base state will tell you which solution to choose, in the sense that you'll pick a solution which is closer to this base state. Yeah. And okay, so how do you implement the previous mechanism?
Gamma.
I'm sorry.
And gamma.
There is gamma. There is a very good thing. Let me see where I put it. Let's put it here. Yes. Gamma. dtx.
And this is part of your h?
Sorry?
This is part of the function h?
This is the extended thing. Yeah? H is just this thing here. Yeah. Okay. And now I'll define the following integrand. Yeah. So I'll write all this thing here, except for the red thing, which is just integral in space. I'll write the integral in time and space as some L curl of let me put L curl of H, yeah, of V bar and D dt dx, and D would be just a notation to say that I take lambda, gamma, but also there can be derivatives of lambda or of gamma. Yeah. Okay. So this is the LH, and really I'm gonna. So let me write what this LH is, and what I'm gonna do is to take that derivative with respect to V, and I'm gonna write get V as a function of this D curl, right? So the goal is, okay, so let's do it like this. There are primal and dual variables. So the primal variables are the unknowns of the original problem. Yeah. These are primal variables. Like the x's before, and then there are the dual variables. These are dual variables. And what I'm going to do is to express these dual, the primal variables as functions of the dual variables, right? Like the x's as functions of z, and I'm going to get a functional just in lambda and gamma. It will be a huge mess, but the critical points of that functional will provide me formally a solution of Euler, yeah, because you know even in classical variation you don't always have critical points, yeah. Okay, so when everything goes well, those critical points provide you a solution of Euler. In this case, yeah, you can do it afterwards for 9 years. Okay, so this LH, what is it? Let me write it first. This. Okay, so the LH is something like this, V bar, and D is not too bad actually. It's the following. Vi, and then you have dt lambda I, is this one here. There is a term here plus di gamma. And then there is something from here, which is minus AV over 2 VI bar. Yeah. Okay. And then I move to the quadratic ones. VI, Vj, and I have this part here. Dj lambda I plus I lambda j. I like to write it in this form because it's more symmetric. Yeah. So this is, let's put it here, over 2 plus, and then there is the v squared term here, which I'm going to write in the following form. AB delta ij. Yeah. So if I take this delta ij, this will be precisely when I do summation over ij. This will be v squared. Yeah. And I don't include the terms 1/2 of ab v squared. I mean, okay, I could include in principle in order to be true there. Okay, that included, but you'll see it doesn't make a difference. I should also include this but these don't really matter because what I'll be interested in is this thing. To take derivative with respect to v of this, and then what will I do and set this equal to 0. Okay?
And what do you say? I see. So
Okay.
D is this set of
yeah, it's just a notation to make this
Okay.
thing more
Okay.
compact.
So you wrote down, make sure that the L that you denote by L is these other parts.
Yeah.
Okay.
Okay. So let's see what this actually means. Okay.
Mm-hmm.
Maybe other ways to this. Okay, so when I take derivative with respect to b, I get something like this. Well, for this part here, so this is equivalent to dt lambda I plus di gamma minus a plus. And I'm gonna have here something like dj d lambda I. Sorry, this is a bit more convoluted. Let me just take it from here. Okay, so it's yeah. Okay, so you see this is coming from here, you know, and then also from here I have this part here, and the rest is coming from this term. Yeah. So in particular, I get this in here, and after manipulating a bit the indices, I have this. Yeah. So what I want now is to do the following, really to have, remember to have VLH dV of, and I'm going to solve this VH as a function of D, and this dot to be equal to 0. So what I want is to find this VI, and let me put an H on it. Yeah. So if I rearrange things a bit, yeah, I'll have the following. I have AB plus lambda partial lambda j plus partial j lambda I. Okay, this is the I. Yeah. That was is equal to minus b lambda minus b gamma plus ab over 2 okay. So these are the h here, and now let me denote this. I'm going to denote this. This is equal to 2 Bij. So Bij is like the symmetric gradient of the symmetric gradient of lambda. Yeah, and I'm going to denote this with Ei. This is a vector. A vector, a matrix. So what I have here is this AB written in matrix form, AB times identity plus 2 times B, this matrix, multiplied by this BH that I'm trying to find, is equal to E. Yeah? And then BH is equal to AB identity plus 2B minus 1 times e. Provided that this is an inverse, which is not guaranteed, we'll have to construct it in such a way. So once we have this dh, if I replace it in here, yeah, I'll have this miracle that I was telling you before. So define SH of D and V bar, which is this SH of hat of V hat as a function of D, yeah? D and V bar, yeah? So this will be just double integral, of this L curl of H D bar, dx plus this initial part, which is as before, b 0x lambda I x 0 dx dt. Okay. And here's the miracle, which is really guaranteed by this. Yeah. Namely, okay, I'm going to erase everything, just almost everything. Yeah, okay so far? And I have the following, the first variation, so let me denote it probably like this, dsh d of this thing here becomes something like this, dh, and then there are in here 3 parts, yeah, so it will be dv and all of that dh d bar, probably something like d d. Okay, so sorry. The third variation is evaluated that these functionals, the lambda and the gamma. Okay, so these is all formal. The dv plus, so dlh and that's it. And then we'll do something for the initial data. So this is time space. And this thing here vanishes. This is just because of this star condition. And now this thing here, what is happening? What were the d's? Yeah. Remember that the d's were just linear. Yeah, the d's were these lambda and gamma. So when I write this, remember LH was something like this. So it was vi and then dt lambda I plus di gamma minus a plus, and then 1/2 dj lambda di lambda j plus dj lambda I, and but the main point is, so these were these, well, I mean, involving just components of d, but these components of d are first order. So when I differentiate them, I formally just get these back, So what I'll, so the point is that what I'll get here after you do all the calculations will look something like this. Will be and of course I'm just shamelessly integrating by parts here. Move the derivative here, I'll have x minus h. Now, so I'll just have that this VIH is satisfying Euler weakly. So this is a formal scheme. So, you get this complicated energy functional that has a property that its critical points are providing you through this nonlinear transformation. Through this nonlinear. So, you have here in E and B, you have lambda and gamma. So these are just a way of writing in a compact form what lambda and gamma are there, but through this scheme you get that critical points of this extended functional are providing you solutions of Euler. And this is not just for Euler, you can do it for virtually anything. And then, of course,
the structure of H place in a row.
What you need is just to be able to solve this equation. So you can put more complicated H things. And of course, once you solve it, you want to be able to say that the dual function that you get will have actually critical points. And it turns out that the dual function that you get when you write it in E and B is a convex function of E and B. So that's what Brenier refers to as a hidden convexity in Euler. So this is quite an interesting story by itself, but let's see.
But okay, so I see the strategy, and now this is very general.
Very general.
Okay, so is there Brenier or there has been does this have been done for any PDE where you get information from, because you're rewriting in the solutions, you're writing it in a different way.
What is this by?
Yes.
Right. Let's see.
So any example of a PDE where you
get something?
You get something?
What you get is a notion of solutions which is weaker than weak solutions. Yeah. So any weak solution will be a solution of this thing, but it's not clear the other way around. Yeah.
Okay, so this gives you a new definition of what a weak solution is.
It's a weaker notion of solution, yeah,
Okay.
which has the potential advantage that it has more structure, yeah. It has additional type of structure for, say, weak solutions, yeah. It has this variational, it comes from a variation principle, so if you take critical points, you also know, say for instance, that you have the second variation is positive definite, yeah. So in principle, you have some additional information on weak solutions. Also, you are, you see, for any base state with V bar, I get this variational dual solution, yeah. So I get a lot of solutions, ridiculously many. For instance, you could do this for the heat equation. And then what you get as variational dual functional is a functional whose critical points give you some sort of fourth order, heat type equation, but it's a wrong sign, so ill-posed. Nevertheless, there is some magic and things work there, and you do actual calculations, and you see that you get a unique solution. Yeah, for all the base state will provide you the same solution. However, if you try to do it for burgers, for which you know that there are several types of several possible solutions, you get you can with this you'll pick just the entropy solution that is
Okay, so for burgers, you gain new information?
I mean, for burgers everything is known, so it's hard to say.
Okay.
But,
Yeah.
So you have a different way, a different criterion for choosing weak solutions when there are several such things.
Mm-hmm.
Yeah. And also, what one other thing that you get is also the implicit limit. If you have in standard for on a torus, you need to have at least some regularity to know that you have a short time existence for Euler for the limit. Yeah, that's kind of what Constantine, but presumably others before. If you know that Euler exists for short time, then on the torus or on the whole space you have the implicit limit. Yeah. So this gives you with much weaker assumptions of the regularity. Yeah. Because you are working with these weak solutions. Yeah. So far there isn't much that is genuinely new information provided by this, but there is a lot of levers that you can pull, namely these base state, and we actually pull them in proving this implicit limit. Yeah. And we did this implicit limit with tools that are specific to calculus of variations, namely gamma convergence. Yeah. So it's a new toy to play with. Whether it will actually buy something genuinely new, that's still
okay.
That's the status.
Okay.
Yeah.
Question: this function h is so you said that in principle what you need is something which makes that matrix invertible, but it is also
not really, but something that gives you, say, a matrix equation that you can solve at this formula.
Is it also a way to impose, L2 constraints or other kind of information about the solution that you would like to capture?
At the moment, no. But in principle, you can add, constraints like will be the energy dissipation, and put them as constraints in your minimization. Yeah. So So yeah, this is still early stages. Yeah.
Still more comment?
To be continued.
Yes.
Tomorrow. So it's time for lunch. So we can continue with that. Thank you, the speaker.